We saw in the last video that work can be converted into gravitational potential energy, and that gravitational potential energy can be converted into kinetic energy. The amount of potential energy gained is equal to the amount of work done on it, and the amount of kinetic energy is equal to the amount of potential energy available. What we see here is that energy can be converted from one form to another, and that the total quantity remains constant. This constant arises from the law of conservation of energy. This law is remarkable in that it states that all energy within a system is conserved and is neither created or destroyed. It merely transforms from one form of energy to another. The law also provides a tool for analyzing and solving physics problems. For example, we can predict how high a pole vaulter can jump based on his running speed prior to the jump. To understand the conservation of energy, its applications and consequences, we first have to know about conservative and non-conservative forces. A conservative force is defined as one where the work done by that force to move an object from one point to another depends only on the displacement and not the path taken. A force that does depend on the path taken is called a non-conservative force. This definition may seem abstract and difficult to visualize, so let's look at a simple example. Consider a playground with two slides that start from the same height, h. We saw in the last video that the gravitational potential energy gained is independent of the path taken to get to that height. So a child can climb to the top of the slide by climbing up the ramp or by climbing up a slide. The distance traveled by each path is different. But whichever path that the child takes, he or she reaches the same height and gains the same amount of gravitational potential energy. So gravity is an example of a conservative force because the work done by or against gravity depends only on the vertical displacement and not the path taken to get there. An example of a non-conservative force is the force of friction. Now that the child is on top of the playground, the child can come back down by taking either of the two slides. Slide A spirals down over a longer length compared to slide B. As both slides are made from the same material, the friction on them that is experienced by the slider is the same. But since slide A is longer, the child experiences this friction over a longer distance. So the work done by the frictional force is more for slide A compared to slide B. Friction takes energy away in the form of heat, so more energy is lost due to friction for slide A compared to slide B. Frictional force is thus non-conservative because the work done by the force depends on the actual path taken and not just the starting and end points. Now let's go back to the law of conservation of energy. We saw in the video on kinetic energy that the net work done on an object changes its kinetic energy. We also saw in the video on gravitational potential energy that the work done to raise an object to some height gives the object gravitational potential energy. In general, the total mechanical energy of a system at any point in time can be made up of either kinetic energy or potential energy or both, and is written as E is equal to K plus U. If only conservative forces are doing work, then the total energy is constant and the energy before the work is done is equal to the energy after the work is done. This is the conservation of mechanical energy. When non-conservative forces are involved, the work done by a non-conservative force changes the energy equation, and the energy before the work is different to the energy after the work. The difference between the total energy before and the energy after is the work done by the non-conservative force. If energy after is less than the energy before, the energy has been lost. Let's have a look at an example. Consider a skater on a half-pipe. The height of the half-pipe is 6 meters. If the skater was initially stationary at the base of the half-pipe, then he has no kinetic energy. And since the base is at 0 meters above the ground, the skater has no initial gravitational potential energy either. If we now raise the skater to the top of the half-pipe, we have elevated him to 6 meters above the base. We have done work on the skater, and he has gained gravitational potential energy equal to his mass times the acceleration due to gravity times the height. The total energy of the skater at this point is the energy gained from this work done. If we now release the skater and he starts to roll down the halfpipe, there's a couple of things that we notice. Firstly, he's losing height, so therefore his potential energy is reducing since gravitational potential energy is proportional to height. Secondly, he's increasing his speed, indicating that he's increasing his kinetic energy. At the bottom of the halfpipe, there is no more gravitational potential energy, but just kinetic energy. As he moves up the other side of the ramp, he begins to slow down as he gains height, eventually stopping at the same elevation as where he started on the other side, that is, at 6 meters. At this point, he will have no kinetic energy and maximum potential energy. So what we can see is that he is converting his gravitational potential energy into kinetic energy as he's going down, and then converting his kinetic energy back to gravitational potential energy as he goes back up. In between the top and the bottom, the skater will have a combination of both kinetic and potential energy. At all times, the sum of the kinetic energy and the potential energy is constant and is equal to the initial total energy. This can be seen in the graph where kinetic and potential energy is exchanging with each other. So at what position along the halfpipe does the skater have maximum speed? At the bottom of the halfpipe, there is no potential energy. This means that all of the energy is converted to kinetic energy. So the skater will have maximum kinetic energy at the bottom of the ramp. Since kinetic energy is proportional to speed, he will have its maximum speed when the kinetic energy is at a maximum. At what height will the kinetic and the potential energy be the same? If you're unsure about the answer, step through the video while monitoring the energy graph for the instant when the kinetic energy and the potential energy are equal to each other. Now we're going to turn on friction and watch what happens to the skater. Again, we'll launch him at 6 meters, but this time we notice that he doesn't reach the same height on the other side. Instead, his highest point is just short of 5 meters, at around 4.8 meters to be more precise. This shows that his gravitational potential energy is less than when he started, and since this is his highest point, there is no kinetic energy, and so the total energy is also less. The difference is the energy that has been converted to heat or thermal energy by friction and is lost. Friction is a non-conservative force. As the skater continues to go down and up the ramp, he continues to convert his mechanical energy into thermal energy. Eventually, there will be no mechanical energy left, and the skater will come to a stop at the bottom of the halfpipe. In summary, the conservation of energy tells us that energy is neither created or destroyed. Within a system where conservative forces are acting, the total mechanical energy remains constant, but may change forms and is equal to the sum of the kinetic and the potential energies. When non-conservative forces are acting, the total energy within the system changes, the difference being the work done by the non-conservative force. A conservative force is one where the work done depends only on the start and end positions, whereas the work done by a non-conservative force depends on the path taken.